and this is joint work with Joe Fon, who is here in the audience, and David Parks, who is not here. So the question we're interested in studying is, what does a profit-maximizing market-making strategy look like when you're facing adverse selection, but in particular, when you're making a market across more than two assets? And when I say assets here, I mean two assets in addition to cash. So in CFMM terms, I mean a curve over more than just a pair. So our question is, how should optimal market-making strategies change potentially in that case when there's more than just a pair being traded? So this is a paper, it's on arXiv now and under review. And the main focus of the paper is just developing the theoretical tools to answer that question. So characterizing this optimization problem and showing it as a dual and how to solve it. But methodologically, something that might be interesting is following a lot of successes in other areas of mechanism design. We treat this as kind of a machine learning problem in a sense. So a mechanism ultimately is just a function somehow, and machine learning gives you really good tools for searching through spaces of functions. And people have called that differentiable economics, if you like buzzwords. So that's what we do here with some success. So the problem we're interested in, normally for a computer science audience, I have to explain what's market making, what's adverse selection. Here I assume people already know what that is, and probably many of you have experienced it at some point. But we're interested in this question of a market maker who has some value that they think is right for a good, and traders are trading with them who might be better informed. So there might be adverse selection. And just to study this problem, the model we pick, which we pick just because it's nice enough, a little bit stylized, but still good, and we were able to get traction on it, comes from this paper by Milionis et al. I believe Jason is also here. This is not the Lever paper. This is a different paper. And what they do is they consider a pretty rich space of market-making strategies. So pretty much all the possible one-dimensional automated market maker curves. And what they show is that even though you have this very rich space of possible strategies, you don't need to use them. The optimal market-making solution under their model always takes the simple form of a bid-ask spread. In other words, just a pair of limit orders. Or in CFMM terms, you should just concentrate all your liquidity in two Uniswap V3 regions. So you have this very rich space of strategies, but in fact, if your goal is to maximize profit under adverse selection, you don't need them. So the question we're interested in is, what happens now when you're making markets across multiple assets? Is that still the case? Here, the space of possible strategies is even richer. And maybe it could be the case that optimal strategies across multiple assets just look like taking the optimal strategy for a single asset and gluing them together, like here on the right. But it could also be the case, and in other multi-parameter mechanism design problems, this tends to be the case, that you need to do something more complicated that allows for bundling or interactions between the different assets. And platforms that support that kind of bundling for market makers or people placing orders on the platforms, they do exist. In the traditional finance world, there are some ATSs or some bond trading platforms that let you do this. There's recently been a lot of interest in the flow trading model by Budish et al. And there are some multi-token pools in DeFi. So this stuff exists, but on the whole, platforms or systems that support this are not super popular. It's not super well explored. So we're interested in how much extra power does this give the market maker. So now, concretely, to describe our model, this is a multi-dimensional version of that model from Milionis et al. We assume we have some market maker making a market in, let's say, two goods or n goods, in addition to cash. And they have some view of what the correct price of those two goods is. And given that price and their knowledge about the market, they make some set of offers. And a trader shows up. The trader has their own view about the price. And they are drawn from some population, which just follows some probability distribution with a density f of x. So the trader picks their favorite trade from all the offers being made by the market maker and they wind up trading a net quantity of goods described by this function A of x at a net price of P of x. And those can go either positive or negative because you could be buying or selling goods. So the market maker's goal is to optimize their expected profit here, this expression on the top right. But they're anticipating adverse selection. And so as soon as they see someone traded with them at prices X, they get nervous and they update their view in the price according to this update function pi. So they wind up sort of booking their expected profit according to that expression. They want to pick a set of offers to maximize that in expectation over the population of trade-offs. You may notice here there's no notion of time in this model, and that's a key limitation of the work we've done. We'd like to extend to a dynamic setting, but it turned out there's more than enough for us to chew on here. Okay, so that's our problem, which we described in terms of this allocation function A of x and payment function P of x. And that's kind of the traditional mechanism design perspective, which is useful because it lets us bring in tools and ideas for mechanism design. There is a direct connection to constant function market makers. It's very, very similar in spirit to the talk you just saw about prediction markets. I think in general, drawing these connections is a really fruitful direction. I'll just sketch out the perspective we took in our paper to make that connection. So just a concrete example with Uniswap. You have the Uniswap curve. It's in some initial state, which is in orange there, and the trader can make any trade that takes you to any other point on the curve here in green. So you can think of all those possible trades as essentially being a menu, and the trader is going to pick whichever trade on the menu they like the most. So supposing they have their own view of the price, like they're an arbitrageur, or at least they think they're an arbitrageur, they don't necessarily have to be right about that. As a function of that price, they're going to pick their most favorable trade, and they're going to make some profit. So on the right here is just the trader's utility function. Sometimes it gets called their information rent. From the market maker's perspective, this is their impermanent loss or divergence loss, but it's just a convex function that's the trader's view of the price and describes the utility they get for making their best trade as a function of their view of the price. So this is always a convex function because the trader is always picking their most favorable trade, so it's a maximum over a bunch of trades. And in the setting we care about, this convex function uniquely identifies the mechanism or the market-making strategy. So here, the sort of initial state of the market maker is 1/2, and so you can see the trader doesn't want to trade if their view of the price is 1/2. They get zero utility from doing that. So that convex function is sort of our canonical view of the mechanism, but you can also easily go from that to these allocation and payment functions. So it turns out the allocation is just the derivative of that utility, and then from there it's very easy algebraic manipulation to get the price as well. So all these things are equivalent. That's the key takeaway, at least in our setting where there's only one trade happening. But to bring in the tools for mechanism design, we tend to focus on these first two. Mainly we're thinking in terms of the trader's utility function as being the thing that defines the market-making strategy. So with that out of the way, having explained our model, what we do in this paper is take tools for mechanism design for showing strong duality for certain mechanism design problems. And we generalize those to the market maker design problem. And then given those tools and given some conjecture of a mechanism, if it's optimal, we can prove it optimal. And to come up with those conjectures, that's where we use this machine learning approach to sort of do a search through the space of mechanisms, which could be pretty complicated, and get a hypothesis of an optimal mechanism. And we get many of those conjectures showing a range of very interesting behavior. And for one family of mechanisms, we're able to actually prove optimality. Okay, so at a high level, these are our theoretical results. I have a bunch of backup slides on these if anyone's interested. But what we're doing is generalizing tools for mechanism design. And it turns out that the problem of designing an optimal market maker. So the market maker's optimization problem over that expected profit objective that I showed before. If you do a bunch of integration by parts, it's not very difficult, but it is a pretty involved and tedious computation. You can rewrite things until you wind up with this problem on the left. So you're maximizing over the space of all utility functions for the trader, the integral of that utility function against this object mu, and mu is just some object that depends on your problem instance. Like it includes information about the population of traders and that update function pi and so on. But that left-hand side there is your expected profit. So given a guess for a good market-making strategy, you can calculate that expected profit, and we show that that optimization problem is dual to a relaxed version of an optimal transport problem. So if we can come up with a matching gamma on the right-hand side, then we know both of these solutions are optimal, and so we've proved our mechanism optimal. That's at a high level. Okay, so now going into how we actually do that, just a lead up of what the space of possible strategies might look like. I mentioned before that one consideration might just be that a simple separate strategy for each good, sort of aggregated together, might be reasonable. And this is what that looks like. So if you have a pair of limit orders here for the apple and a pair of limit orders for the orange, and we want to visualize this mechanism in terms of those allocation and payment functions, you wind up with plots that look like this. So the allocation of the apple, you can see as the trader's value for the apple increases along the x-axis, they move from selling the apple to the market maker to not trading it at all to buying it from the market maker. And the same thing happens in the plot for the orange, just now moving along the y-axis. And then combining those two decisions together by the trader, they wind up making payments that look like that. And in the middle, there's a no trade region. So traders whose values for the apple and the orange fall into that region, they don't like any of the possible trades with this mechanism. So they'll choose not to trade. And that no trade region tends to show up in all of our solutions, and it's like the analogy of the spread in the one-dimensional case. So this is one possible strategy, reasonable seeming one, but we want to search through this much richer space of strategies and see, is there something better? What might it look like? So the way we do that is to borrow tools from machine learning. In particular, there's been a lot of success applying machine learning to problems in auction design. We take one of those, a method called RochetNet, and we modify it. So RochetNet is named after Rochet, who showed in a paper a while ago that all truthful mechanisms can be identified with convex utility functions. And every convex function is just a max over linear functions. So you can represent a convex function that way. But what you actually have in that case is just a very shallow, very simple input convex neural network. So if you want to optimize in this space, you can train it as if it's a neural network. And that's not a convex problem, but if you do things right, over-parameterize everything and just run it on a GPU, it still works really well. In fact, even though it's not guaranteed, we typically do get either to the globally optimal solution or at least very close. So we do this, we train these things, and here are some of the outputs. What we wind up with are market-making strategies that look very weird and not at all like that simple idea of having pairs of limit orders for each good. So on the top right there, you can see a market-making strategy that is totally unwilling to trade in each good separately. It only will let a trader interact with it if they're trading in both goods at once. On the top left, you can see a similar strategy, but now it has kind of these blurry regions. So those are regions where the allocations are varying continuously with the trader's price. So that's something that's in the space of market-making strategies, but in the one-dimensional case, it turned out to not be useful. All you need in the one-dimensional case for optimality are limit orders. But here, for optimality, at least we conjecture, you do need this continuously varying curve. And then we also, in some cases, find strategies that kind of both bundle and trade separately, but with price improvement for the bundle. And then everything we do in the paper works for any number of assets. And so just to see what would happen, we ran this on a 3-good case, so that would be a 4-asset CFMM curve. And we found this very weird structure where the no trade region in the center now takes the shape of a polyhedron. Okay, so those are conjectures that we generated using machine learning. And for at least one family of mechanisms, we were able to actually analytically prove optimality. So here, for the case of a uniform trader distribution, where there's adverse selection happening, according to this simple model, which comes from the Milionis paper, where lambda parameterizes the strength of adverse selection. So lambda is like the parameter saying, how much do I think I'm right about the price versus my counterparty? So in all these cases, whatever the strength of adverse selection, the optimal mechanism winds up taking the form of a bid-ask spread for each good, but then also discounts being offered to trade in the bundles or to make payments in kind. In other words, you want to buy an apple, you can trade in an orange, and you can get a better price that way than if you just bought the apple and sold the orange separately. So that structure remains always, but as adverse selection gets stronger, the prices get worse and worse, and the mechanism gets less and less willing to trade. So here, for this family of mechanisms, we've actually proved this is what the optimal market-making strategy looks like. So that's our takeaways here. At least under this model, optimal market-making strategies might require interactions between the goods. Just separately trading pairs or having a network of pairwise CFMMs is not enough. It's, at least under this model, leaving some money on the table for the market maker. So that's a concrete takeaway there. I think probably there should be more interest in multi-asset pools and multi-asset trading on exchanges. Independent of that, we have these computational tools for designing automated market makers, which are pretty easy to use and work quite well and might be of independent interest. And our theory is for this simple model, which we just picked because it's interesting enough and something to work on, but it's fairly modular, and you could probably drop in a lot of other objectives, a lot of other goals for the market maker. So those are all possible future directions. More broadly, as we've seen with the last talk, there's a very rich literature in mechanism design, and I think a lot of it still has not been mined for DeFi, and people should be looking at it more. I think there's a lot of opportunity there. That's it. Any questions?
So you posed a conjecture that said something like that in one of the cases, you will require having kind of this continuous trade, right, happening.
Yeah, top
somewhere
left
in the
here.
middle. Why should we believe that, right? Like the objective that you have looks very linear and looks like a bang-bang type theorem might apply. What should be intuitively the reason why we must require this kind of like continuous trade? I don't know if you
have
thought
any
about
intuition for this.
Okay.
You can look at the paper. It just, I don't know. There's very little intuition for.
Yeah, because the objective looks like you could do like a 0-1 principle on it or something, right? Like standard control type argument.
So in general, in multi-parameter mechanism design, that tends to not be the case. It's very challenging for us to come up with a dual solution there. We certainly tried to prove it optimal, but I'm pretty sure this is right. It would be a surprising thing to fall out of this optimization pipeline if it weren't useful. You would expect the neural network to find the bang-bang solution there.
Interesting. Thank you.
Yeah? Under our model, yes, they are making a profit. Yes. We've thought a lot about that. It makes the problem even gnarlier than it already is. I guess the simplest form of competition I could think of is where your competitors are just out there and they don't have the opportunity to best respond to you. You can see them and design your market-making strategy. There, I think we could incorporate that as a constraint on the allocations the market maker is allowed to make. And then we might be able to get optimal solutions. So I think the theoretical framework could be extended, but I don't know what solutions would look like. What? I don't think there's much connection at all. We don't have any notion of time there.